All right, well, welcome back, BC folks. We're continuing on Taylor polynomials and Taylor series. This is a reminder of what we talked about yesterday. You can approximate a function, an interesting function like sine or e to the x or tangent or log using this format. Remember, we showed yesterday how using the calculator that within a window centered at a certain point, we could have a polynomial very closely approximate the sine function. Same thing would go for other functions as well. So we're starting out with f of c plus the first derivative at that same value c, so centered at c. So some of the examples were centered at 0. We call that a Maclaurin series. Times x minus c plus the second derivative. So I'm not sure if it comes through on the print there, but f prime prime hash hash, the second derivative at c times x minus c squared over 2 factorial plus the next term would be the third derivative at c times x minus c to the third power over 3 factorial, etc., dot, dot, dot. The nth derivative at c divided by n factorial times x minus c to the nth power plus dot, dot, dot. So, well, that could go on. Now we're adding this term over here, the summation term. So we have sigma from n equals 0 to infinity of n factorial on the bottom, the nth degree, so f prime of 0 would just be f of 0, right? It's not the derivative, but the function there, x minus c to the nth power. Well, when n is 0, that'd be to the 1 power, so just x minus c. So you've got that there. So the summation term, something new that we didn't have yesterday. So we'll do another one that we started similar to yesterday. Find a Taylor series, f of x equals e to the 5x, centered at c equals 2, give the first 4 non-zero terms and the general term. So I'm going to start out with a table, and this is how I would recommend that you do this if you have to build up one that you don't know. We'll revisit that in just a second. We're talking about e to the 5x, so e to the 5x. And then I need a bunch of derivatives here, and I'll know when to stop when I need the first 4 non-zero terms. So depending on how far I'll get, we'll get those 0 terms there. So what's the derivative of e to the 5x? Well, e to the x is e to the x derivative, but e to the 5x is going to be 5 e to the 5x. The second derivative then, 25 e to the 5x. The third derivative would be 5 times 5. Isn't that 125? E to the 5x. And then just for good measure, remember we stopped the hash hash hash, but prime prime prime, but parentheses, the fourth derivative at x. 5 times 125, well, 625 e to the 5x. Okay? However, I need this centered at c equals 2, so I'm going to evaluate each of those, f of 2. Well, that's plug in the x there, we get e to the 10th. F prime at 2, that's going to be 5 times e to the 10th. F prime at, f double prime, the second derivative, 25 e to the 10th. And the third derivative at 2 is going to be 125 e to the 10th. Okay, we'll see if that's enough there. Okay. So let's go ahead, and we want our first 4 terms. So what degree would that be? First 4 terms, if we've got f of 2, that's not 0, so we're going to have a third degree polynomial here. I'm going to start out with e to the 10th plus 5 e to the 10th, that's my f prime at c, times x minus 2, that's my x minus c there, right? Our next term would be plus 25 e to the 10th times x minus 2 squared, but I need over 2 factorial, and I need to squeeze in another term here, so plus 125 e to the 10th over 3 factorial times x minus 2 to the third power. This is the third derivative over the third factorial, 3 factorial, times x minus 2 to the third power. Okay, all of these should synchronize there. Let's go ahead and do the summation term. So we should be able to quickly enough see this. If you're not seeing this, use the indexing number. This is e. Remember, this is going to be from n equals 0 to infinity there. So we've got to think about what the terms would need to be there. Well, it'd be 5 to the, do you see any, well, sometimes this one, in fact, let's start with this one. Sometimes it makes sense to skip the 0 term. This is 0, this is 1, this is 2, this is 3. Okay, so think of the first one first. I think it's easier to see the pattern, and then we'll go back and check the 0 term. All right, because we are starting this index at 0. We're starting that index at 0 to infinity. Let's start with the, it looks like we've got 5 to the nth power here, doesn't it? Because we've got 5 to the 1, 5 to the 2, 5 to the 3, 5 to the nth power. All right. The next one, we've got e to the 10th in all of these, so that's just e to the 10th. So let's put that in there. And then I do have x minus 2. Well, this would be the first power, second power, third power, so that's to the nth power. And then what else do I need? Divided by n factorial, because that's to the 1 power, right? If you need to put a 1, or sorry, over 1 factorial, 2 factorial, 3 factorial. 1 factorial is 1, that's no biggie. Let's check now that this makes sense for the 0 term. What is 5 to the 0? 1. What's e to the 10th? E to the 10th. What's x minus 2 to the 0 power? 1. What is n factorial when n is 0? Well, by definition, 0 factorial is 1, so this works for the 0 term as well. That's why when I pick these, I would start out with your indexing, 1, 2, 3, but skip that 0 and then just double check that it still fits. Okay? So that's the summation term. That would be called the general term. The general term. Okay? So you've got the first 4, 1, 2, 3, 4, check, and the general term, the summation. Okay? That's your general term. Okay, now there are 3 special Maclaurin series that you must know, and there's more than just these 3, but these 3 show up so often that you're going to want to know these, because you'll see when we turn the page that you can build a lot of other related ones from this point. So we've used e to the x before. Well, we had e to the 5x. I think we had e to the x as an example yesterday. Okay, so the e to the x is just this. I'm going to say the approximation, e to the x equals 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth. I think we can see the pattern here, so we're going to say dot dot dot. And then I'm going to use equals the general term, n equals 0 to infinity. And you should be able to see this. I don't even memorize these, to be honest. I do memorize these. And it comes back to me every year as I teach it every year. But I would have these memorized. I would not have this memorized. Okay, I wouldn't worry about this because you can always get the general term. If you need to, put your indexes right above. 0, 1, 2, 3, 4. Okay, for this first one, I'll do just that so you can see it. You know, do it in pencil so it's nice and light there. But gosh, it looks like x to the n, doesn't it? Does that work for the first term? It sure does, because x to the 0 is just 1. Divided by, well, it looks like n factorial to me. And sure enough, it is. So we've got the sum, that's our general term, the sum from n equals 0 to infinity of x to the n over n factorial. Sine of x, we derived this one yesterday. Or no, I think we showed this one. We derived cosine, but these, and again, are in your textbook. There's a bigger table if you want to memorize those. As you're compiling your information to get ready for the AP test, especially in this year 2020, you might want to have those handy and ready to go. So, you know, have your book handy. Sine of x, is x minus x to the third over 3 factorial plus, this one's an alternating one, x to the fifth over 5 factorial minus, I'll do one more term, x to the seventh over 7 factorial plus dot dot dot, because we're going to see that that pattern continues. Well, our general term for that is n equals 0 to infinity, the summation of those, sigma of that. One thing I see, I've got a negative number. So I've got -1, and I just have to get the signs to work. So remember, this is 0 term, 1 term, 2 term, 3 term. The odd terms are negative, so that'll work. -1 to the nth power. Then I've got x to the 1, x to the 3, x to the 5. These are going up in powers of 2. So it's x to the 2n. But is it really? Because, I don't know, I might have to... Remember, this is 0. This is 1. Again, make those indexes if you need to. Right? This is our 0th term, our first term, our third term. So even though this is the third degree, this is the first term. This is the... or n equals 1. It's really the second because we're starting our count with 0. I need 2n plus 1, don't I? Over what factorial? Well, that's also going to be 2n plus 1 factorial. Okay? And cosine x. Okay? Is alternating again, but it starts this time with 1 because f of cosine, and again these are Maclaurin series, so these are centered at 0, so that's why there's no x minus, so you could build up from there, but the patterns are all going to work for you. Minus x squared over 2 factorial, this one's alternating, but it's all the even terms here, that's interesting, minus x to the 6th over 6 factorial, and you could continue that on. Dot 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 equals the sum n equals 0 to infinity. I have a -1. The first term is positive, so again, -1 to the nth power is going to work. Then I've got x to the 0, x to the 2, 4, 6. This is x to the 2n, isn't it? Over 2n factorial. Some observations. Easy way to remember this. E to the x. Is e to the x an ever increasing function? Whoop. Sure is. All those are pluses, huh? E also starts with everything. E for everything. It's all the terms, all the powers, all of them are there. Interesting. Sine of x, I don't know if you've noticed, these are all the odd powers and odd factorials for to build up the coefficients. Is sine an odd function? Think about that. Origin symmetry much? Cosine, even better. Does it increase and decrease and increase? So it's a plus minus, so it's alternating again. So like cosine, it's plus and minus. But this one has all the even powers. Is cosine an even function? Yeah. Coincidence? I think not. I think math is pretty powerful. I get chills thinking about how that's easy to think about. So I hope you do too. All right? So have these memorized. Have these memorized. At least these 3. Because it will help you. How's it going to help us? Well, I'm going to keep this handy, but I'm going to go to the next page and say you can manipulate those 3 special trig or any series that we're given, because sometimes we're given others, okay, to find other series that are related to that. You might be able to substitute into a series. You might be able to multiply or divide that series by a constant or even another variable. You might be able to add or subtract those 2 series. Steps 4 and 5 are also pretty cool. We won't get to those today, but you could take the derivative or integral of a series. So they give you 1, take the derivative of that, or build up this minus that and then take the derivative, or recognize the series as a sum or a geometric power series. This is a really powerful one. Not to use the pun there, power. Not tested this year on the AP test, at least I don't think, but I'm still going to teach it because I think it's pretty important that you'd be able to see these. So this looks scary. Oh, the sine of x squared. This looks hard. No, all I'm going to do is refer to this right here. So, right, I just did and said, oh yeah, memorize this one, so I've got it memorized. I want the sine of x squared. Well, first I'm going to start with sine of x, and that equals x minus x to the third over 3 factorial, plus x to the fifth over 5 factorial, minus x to the seventh. Sure enough, it's the and I want the first 4 non-zero terms and the general term. But I don't want sine of x. I want sine of x squared. I want sine of x squared. So wherever I see an x, I'm going to replace x squared. So that equals that squared. So I'm replacing this right here with x squared, and this right here with x squared, and this right here with x squared, and this right here. You get the idea. So this is x squared minus x squared to the third over 3 factorial plus x squared to the fifth over 5 factorial minus, and I need the first 4 non-zero terms, so I need one more term and the general term. I'll work up my solution here with that. Again, that's why I don't really memorize those general terms. I just build them up over 7 factorial plus dot dot dot. Let's clean that up before we worry about figuring what your next term would be. That's x squared minus what? X to the sixth over 3 factorial? Cool. Plus x to the 10th over 5 factorial? Cool. Minus x to the 14th over 7 factorial plus dot 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 equals the sum. Well, it always starts with n equals 0 to infinity. I have an alternating number, so I need alternating sign. -1 to the n will work. Do you notice that these powers of x are going up by 4s? I'm going to pause and get a drink of water here. All right. Did you notice these powers of x's are going up by 4? From 2 to 6 to 10 to 14. So they're going up by 4. So it kind of reminds me of the slope of 4n. But then if I do when n is 0, I need somewhere to begin, right? So when n is 0, I need plus 2. Would that work for this one? Sure, because this is the first term, the second term, the third term. Granted, this is the 0th term. We're starting our count at n equals 0. So that would work. And then I've got 3 factorial. So 0, 1, 2, 3. Isn't that just going to be 2n plus 1? It's going up by 2s. But I need to start with 1 there over 1 factorial to make this a 2. And again, if you're not seeing it, put 0, 1, 2, 3. The 0 term oftentimes is more confusing. So start with 1. We can all figure it out 1 and then check with the 2 term. Okay? That works. Yeah, 2 times 1 plus 1 more. 2 times 2 plus 1 more. 2 times 2 times 3 plus 1 more is 7. Check. Okay, that'll get you your general term. So again, I hope now you can see that just using your patterns, you should be able to count up and get those general terms there. Find the Maclaurin series for g of x equals x cosine of x. Well, we saw yesterday, just on the previous page, not even yesterday, right? That cosine is 1 minus x squared over 2 factorial, so I'm going to build it up from that. But I don't want that. I want x cosine x. So g of x equals x, and then I'm just going to fill in the cosine function. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot dot dot. And I'm going to leave it like that because I'll get my general term in a bit. Well, because remember we said g of x equals x times the cosine of x. So what I just underlined, cosine of x, is all of that in parentheses. Well, g of x then equals, let's just distribute that, x times 1. So I'm hoping that you're starting to see, oh wow, it's easy to multiply by a variable, divide, take the derivative, because each of these terms are separate. You know, there's no product rule that you need to worry about here. X minus x to the third over 2 factorial plus x to the fifth over 4 factorial minus x to the seventh over 6 factorial plus dot dot dot. So we got our first 4 terms, yay, first 4 non-zero terms. And then I'm going to build up n equals 0 to infinity. And let's see, we'll start with 0, 1, 2, 3. So it looks like we got 2n factorial on the bottom. So sometimes it's easy just to start with what you know, right? Because that works, we see that. Also, I have a negative 1, and it starts out positive, so it'd be, and the odd ones are the, so that would work, negative 1 to the nth power. Then I've got x to some power here. These are going up by 2's. It's going to be 2n, right? Because I've x to the first power, third, 5. So this is x to the 2n. But 2 times 1, how do I get to 3? Well, I'm going to add one more. 2 times 2, how do I get to 5? I'd add one more. So 2n plus 1 is your exponent for the x. So negative 1 to the nth power times x to the 2n plus 1 over 2n factorial. Last one. So we did an example where we substituted x squared. This was case number 1 up here. Substituted x squared in for x. We did another one where we've multiplied or divided. We multiplied by x, a variable, times an existing one that we've got memorized, cosine x. Now we're going to maybe combine. Actually, we need to build up what e to the negative x looks like, right? So I'm going to add e to the x, which I already know. I'm going to create e to the negative x by replacing that, add those two and divide by 2, find the first 4, and then the general term. So let's recite what e to the x is. We have that from the notes on the previous page. We did that one yesterday too. 1 plus x squared over 2 factorial plus x to the third over 3 factorial. I'm just going to get it started because I don't really know how far I'm going to need to go. I'm going to build up e to the negative x. Well, I don't see anything there, so that's 1. I'm replacing that x with a minus x, so I can do that. I'm replacing that x with negative x, but I'm squaring it. So negative x squared is plus x squared over 2 factorial plus what? X to the negative third, right? But I'm sorry, not x to the negative x to the third. So negative x times negative x times negative x is minus x to the third over 3 factorial. Okay, so then I could say e to the x plus e to the negative x. Well, combine like terms. 1 plus 1 is 2. X minus x, meh, plus 2 x squared over 2 factorial, meh. Can you see what's happening here? So I need to get another term, don't I? Because I've only got 2. So maybe the even powers are going to be what survive. So our last step would be e to the x plus e to the negative x all over 2. So what's 2 over 2? That's 1. What's 2 over 2? That's also going to be 1, but x squared over 2 factorial. Well, what's the next term? Aren't the x to the third's going to go away? Then I have 2x to the fourths divided by 2 would be x to the fourth over 4 factorial. The x to the 5 term is going to go away because it's a plus and a minus because the negative exponent, or the odd exponent made that a negative term. Plus x to the 6th over 6 factorial. Is that 1, 2, 3, 4 non-zero terms? Check. Okay. Plus dot 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 equals the sum n equals 0 to infinity. And again, I seem to put this 0, 1, 2, 3. I think you can see that happening here, right? There's no plus 1 minus 1, so I don't have to worry about negative 1 to some power. Again, starting with this first term, this is the 0 term, but starting with term when n equals 1, how do I make that a 2? How do I make that a 4 compared to the n value? That's just x to the 2n over, how do I make, oh, it's the same thing, 2n factorial, and check to see that it works for your x to the, your 0 term. It does, so there's your thing. So I will have a worksheet available for tomorrow for you to practice. Maybe a new lesson on Thursday over this, but at this point I believe this is really the scope of what I would expect to see. I'll double check. We'll still continue to learn more, but I want to make sure that that you're good to go on these types of problems, because this definitely is fair game for how I'm reading what could be on the AP test. And stay tuned as they release example questions. All right. Hope everything is well. Stay well. Do some homework, and look. As I am condensing and deciphering the new guidelines, because I'm sure you all saw an email about that too from Dr. Merle. Grade guidelines, there's going to be one each week. It's going to be a daily grade. I'm going to convert the test to a daily grade for last week. That may actually cause a little bit of change in how you do your preparation. A lot of you typically throughout the year, especially as senioritis hits in, use the discovery method to figure out what's going to be on the test by not preparing at all for the quiz, and then hoping that for the most part the tests will be similar to what the quiz questions were, and especially in this online mode it has been pretty similar. So you didn't do any preparation at all. That's not going to work now, because everything's going to be evenly graded. So each week you'll have one grade, and it'll all average out at the end. So keep that in mind. You want to do a little bit of preparation. I don't think that this is going to be all that scary. So don't make this any harder than it needs to be. Just keep working. All right? But hope everything's well. Please reach out to somebody if you know they're having trouble, because if I don't know anything, I can't really help you either. So hope everybody's doing well. Take care and do some homework. Talk to you soon. Bye.